All right, symbols. So if you look up here, we're going to have to be comfortable using arrow notation because we're going to be using it throughout the entire course. So below are some of our arrow notations. So as you look right here, it says X as X approaches a number from the left. That's what that negative means at the top, that you're approaching it from the left, okay? Here it says X arrow A plus. What that means is X approaches A from the right, okay? So we're getting as close as we can to A, and we're describing what is the function doing, right? Is it approaching a value? Is it increasing? Is it decreasing? What is it doing? Here it says X approaches infinity, and that's positive infinity, which means that we're heading to the right. Does that make sense? I'm heading to the right. X approaches negative infinity, which means I'm heading forever to the left. F of X approaches A. When you see F of X, you're now describing your Y value. What is your Y value doing? The output. Okay, the Y value of the function is approaching A. Okay, that's what it's asking. What is the Y value approaching? This is going to be really useful when you have a horizontal asymptote occurring or a slant asymptote. Here it says F of X approaches infinity. This is where you're describing your end behavior, right? Or your value of your Y. Y is either forever going up or forever going down. And that's what we're describing in there, okay? All right. So with that being said, we're now going to move into our horizontal and vertical asymptotes, okay? Your vertical asymptote. So in the past, we learned that our vertical asymptote is what? Let's talk about it. It's what? It's a domain restriction. It's a restriction on our function, right? A discontinuity, right? It's that imaginary boundary that exists. Vertical asymptotes are defined as X equals a number, right? X equals A. Some unknown number is what we're going to define it as. The graph behavior will approach the vertical line and either increase or decrease without bound, okay? So when we're saying without bound, it's saying that it's either going to forever go up or forever go down. So we use this graph here, and it says, when I'm looking at this graph, I'm going to model it, but here, so it's either going to be plus or minus positive infinity, plus or minus positive infinity is what you're describing your asymptote behavior. Okay. A horizontal asymptote, horizontal is what? It's going to be Y equals a number, right? Remember we talk about OIVUX? Horizontal is Y equal, vertical is X equal, okay? This is the graph behavior will approach the horizontal line as X tends to negative infinity or positive infinity. That's a weird looking infinity symbol right there. It got funky.
It's all right.
Okay. So using our graph that we have here, we're going to analyze what's happening. Okay. Starting here, we're going to find our asymptotes. Our vertical asymptote, hopefully you can see it, is at it's here at X equals -3. Do we all agree? Okay, so we have a VA at X equals -3. It sounded weird. So when we're describing what's happening here, so when I'm describing the left-hand behavior, so I'm going to write the limit as X goes to A from the left. What is the function doing? F of X. Oh, my pen. Why does my pen only do this in your class period? I have no earthly idea. I think so. F of X is doing what? So it's heading towards positive infinity, right? And this is on my left-hand side, and I know it's left-hand because it's A to the negative. And for this problem, our A is -3, correct? Analyzing it from the right-hand side, so I'm going to write it as the limit as X goes to -3 from the right. What is F of X doing? What is our function doing? It's going down, so it's heading towards negative infinity. How do you feel about describing in asymptote boundaries?
Wait, is the only first one, is it at the top of the middle, or-
This would be -3 right here.
But what's the, like, that?
I made an A because I was mimicking this. And I said, here our A is -3.
What's the little thing?
F of x goes to infinity.
No, the thing by the A, like the one.
X goes to A negative
Yeah, why is it a negative?
because you're coming from the left. So on our, go back to our chart. If I have A to the negative, I'm approaching it from the left. Okay. If I have A plus, I'm approaching it from the right. All right. So I want you at your table, take a moment, see if you can identify our horizontal asymptote and describe what's happening around our horizontal asymptote. If you don't feel confident in your writing, then talk it out and we will write it out together. Did he say 7? You were being funny, right? So our horizontal asymptote is at 2. Do we all agree? So I'm gonna do a little. That's the straightest line. Good job. Someone's trained you well, Anthony, on acknowledging straight lines. Good job. All right. So when I look here, I'm now going to describe what's happening with my y equals b. So if we look right here, it says the limit as x goes to negative infinity, what is f of x doing? So now I'm using my horizontal asymptote, right? So as I'm going to negative infinity, I'm trying to reach this horizontal asymptote, right? I'm trying to reach the horizontal asymptote at y equals 2. So that is my limit. Does that make sense? I'm heading towards it. On this side, it says as the limit goes to x goes to positive infinity, what is your function doing? So I'm heading towards positive infinity. And again, what is my goal on this side? I'm trying to get to 2. Okay. The reason why your horizontal asymptote can have a numerical limit is because it is possible to cross a horizontal asymptote. Okay. It may be forever down the line, but it is possible to cross the horizontal asymptote on one side of it. Okay. Because it's just that one little thing that gets across the border. Everything else, failure. But there's one peak in the graph where we allow it to cross. Okay. Y'all are 100% childish. Okay. But the graph does not have to have the same behavior on both sides. Okay. So again, I can cross, and sometimes I do, and sometimes I don't. But in our window, do we see this function crossing? No. So therefore, we are approaching, trying to get as close as possible to 2. Okay. So our horizontal asymptote is setting our limits as we go left and right. Our vertical asymptote is describing our behavior as we're heading towards that asymptote. Okay, our limits of our vertical asymptotes are describing that behavior as we're heading towards it. Okay, now this is going to be key. How many of y'all ever seen like Mean Girls that says the limit doesn't exist? Yep. Nobody? Yeah. Okay. Anyways, so there's a part of the movie when they say this, and this is an example of when the limit doesn't exist. And the limit doesn't exist is because your left side and your right side are not both doing the same thing at that intercept. Does that make sense? Yeah. Yes. So if they were both heading, that's the limit of infinity. But because they're approaching, your left and your right have to be approaching the same thing. Otherwise, the limit does not exist. Okay. And that's what tends to happen in a lot of functions sometimes. All right. So next, how do you find the horizontal asymptote given a function? We can do it from a graph. Were we comfortable finding that y equals 2? Yeah, we can see what it's approaching, right? Now, the question is, can you do it from an equation? And the answer is yes, you can. There are rules. There are rules that we follow. Okay, so it's between your degree of your numerator and the degree of your denominator. So if the degree of your numerator is less than the degree of your denominator, then the line is going to be automatically y equal 0 is your horizontal asymptote. So for example, if I had y equals x minus, Ren, give me your favorite number. 4 over x squared. Carlos, give me a number. 8. Minus 8, right? So notice here that the degree of the numerator is 1. The degree of the denominator is 2. Because the degree of the numerator is smaller than the degree of the denominator, I'm going to have a horizontal asymptote at y equal 0. Because the degree of the numerator, the highest power of the numerator is 1. The highest power of the denominator is 2. So the numerator is smaller than the denominator. I'm going to have a horizontal at y equals 0. Okay? Now, if the degree of my numerator equals the degree of my denominator, if n equals d, then I'm going to have a ratio. Okay, it's going to be y equals ratio between your leading coefficients. So y is going to equal the ratio between your leading coefficients. So for example, if I had y equals 4x squared divided by 8x squared plus 2, notice that the degree of my numerator is 2, and the degree of my denominator is also 2. So their degrees are the same. So therefore, my horizontal asymptote, my HA, horizontal asymptote, is going to be at y equals, and a ratio just means a fraction, right? A comparison of the numerator to the denominator, their leading coefficients. So 4 over 8, which reduces to 1/2. So I will have a horizontal asymptote at y equals 1/2.
What is the like that is why
Y equals,
at the bottom of the response on the
oh,
bottom?
sorry. It is the A over B, just any numbers. Yeah. So A is your leading coefficient. Don't know why I did that, of your numerator. And B is the leading coefficient of your denominator. Thank you. I was distracted by someone playing a game while I was trying to teach.
Wait, so it's just a number?
So it's just a number. All right. How do you feel about case number 1? Good. Case number 2. Doable? All right. Case number 3 is when the degree of the numerator is greater than the degree of your denominator, the graph has 0 horizontal asymptote. There's no horizontal asymptote. I guess I should write the word no and not 0. No horizontal asymptote. See how that converted? Okay. It actually has possibly an oblique asymptote, oblique or slant asymptote. Okay. So an example would be y equals, and give me a number. 16? 16x squared. Anthony, give me another one. 5x. Shayla, give me a number.
3.
Plus 3. All over. Claire, give me a number. Plus 10. Okay, so now when you look at this, notice that the degree of my numerator is 2, and the degree of my denominator is cast with a friendly 1, right? And so now the degree is larger, which means that I don't have a horizontal asymptote, but I have a, a slant or oblique. And how do we find this? This tells me that I'm going to have to use long division to find my slant. So to find that slant or oblique, I would have to do long division.
You just use synthetic and do it.
Or synthetic. You surely can. I don't think this one's going to work out smoothly. I just made up numbers with the class. But we will do an example where we'll do division. Okay. So long division or synthetic if it's a linear situation. Okay, the key thing here is that there only has to be a degree separation of 1. Does that make sense? So this is only bigger by 1 and for there to be a slant. If it's bigger by anything else, then we got a problem. All right, let's practice. So I'm going to give you 3 examples. On example 2, you're going to have 3 areas, and I want you to classify whether it's case 1, case 2, or case 3, and identify if you can. Okay, so you're classifying, talk it out with each other, ask for help. Example 2A. Is it a case 1, case 2, or case 3? It's a case 1. So because it's a case 1, that means that we know that the degree of the numerator is less than the degree of the denominator. So our horizontal asymptote is where? At y equals 0. So then and therefore, I'm going to be professional. Then and therefore, our horizontal asymptote is at y equals 0. Okay, B. What case is that? It's a case 2 situation. Good job. And that means that our degree of our numerator equals the degree of our denominator. So then and therefore, our horizontal asymptote is y equals the ratio of our leading coefficients. So our leading coefficients are what? 3 over 1, which equals 3. Yes, Andrew?
What are the 3 dots beside?
It stands for then and therefore. So in conclusion, or I can now state this, right? It's just so remember, mathematicians are actually lazy people. We try to find the quickest way of doing stuff, shortest amount of writing. And so this was established a long time ago to represent then and therefore. So we don't have to write then and therefore. All right. And by default, what is example C? But not just by default, it's because the degree of the numerator is greater than the degree of the. So then and therefore, there is no horizontal asymptote. Okay. So do we have the green light to move on from horizontal? Yeah, we're good. Questions, comments, concerns? My quiet ones, we're good over there? Yeah, yeah. I said quiet ones. What's up, Andrew? Are you good?
Yeah.
All right, so now we're gonna go on to our slant and oblique, okay? A slant or oblique asymptote occurs when the degree of the numerator is 1 higher than the degree of the denominator. The key thing is what? 1. It's only 1 higher, okay? The slant asymptote is the quotient polynomial found by using synthetic or long division. So you can use whichever one you want. It's totally up to you, okay? So let's analyze. The degree of our numerator here is 2. The degree of our denominator is, cast for the friendly 1. So this is higher. Because this is only a 1 difference, right? It's only higher by 1, then I'm going to then proceed to find long division to find the slant or oblique asymptote. Okay, I'm going to model both. I'm going to model it with long division and I'm going to model it with synthetic. Is that cool?
Yeah.
All right. I don't know if you have enough room on your paper, but here we go. So with long division, you're using everything, right? I don't get rid of nothing. So we have x plus 5 divided into x squared minus 6x plus 7. When we divide, we start with our leading terms. So we have x squared divided by x, and that gives us x. We divide, multiply, subtract, bring down. Divide, multiply, subtract, bring down. So now I'm going to multiply. X times x is x squared. X times 5 is 5x, right? When you subtract polynomials, that means you're changing their signs. Yes.
How did you get the x?
You divide and then you multiply your quotient times your divisor.
So you divide the first x.
So I multiply x times x, which is x squared. X times 5 is 5x. And when you subtract, that means you're changing the signs. So this was a plus, it became a minus. Subtract. And now I'm left with negative 11x And then we bring down plus 7. And you repeat. Okay, so again, I'm gonna now divide. So I'm dividing negative 11x divided by x is 11, negative 11, right? After you divide, you're gonna multiply. Negative 11 times x is negative 11x. Negative 11 times 5 is
55.
negative 55. You divide, multiply, subtract. When you're subtracting polynomials, you're changing their signs. So plus, plus, combine. And we're left with 62. So this is my remainder. So this is written as plus 62 out of x plus 5. Your oblique is just your terms before the remainder. So our oblique asymptote or our slant is at y equals and whatever is in the beginning. X minus 11. So that's my oblique asymptote. Yes. Okay, now in terms of synthetic, so we're going to do synthetic, and synthetic only works if you're, yes, oblique y equals x minus 11. So now when we do synthetic, this can work because our divisor is x plus 5, which is linear. Synthetic only works if it is linear. The first thing you do is take your denominator and set it equal to 0. And that gives you x equals negative 5. That is what you're going to use for your synthetic division. So synthetic division set up, I have negative 5. For synthetic division, you're only writing your coefficients and constants. So we have 1, negative 6, and 7. You get it going by bringing down your first coefficient, and you multiply diagonally, add vertically. 1 times negative 5 is? Negative 6 plus negative 5 is? Negative 5 times negative 11 is? A negative times a negative is a positive, and 7 plus 55 is 62. And again, this is my remainder. These are the coefficients and constant of my solution. So our solution is y equals 1x minus 11. You have two means of finding the exact same thing. Which one is your choice? One has to be. So synthetic is usually mine too. I don't blame you. You multiply diagonally, write the product, add vertically, find the sum, multiply, product, add. Yeah. So it's x minus 11 because when you divide, you're taking an x away, right? I'm factoring an x out. So if I start off as x squared, when it's all said and done, I'm down to just x. So now you just start from x. All right. What time do we leave? 35? Okay. So here we go. Really quick. Finding holes, vertical asymptotes, and x-intercepts. So all of this kind of goes together and ties into multiple TEKs that are expected from AP College Board. So we have rational functions in there. Guys. So key thing is a rational function is a function with a variable in the denominator, right? That's the number one thing. It's a function with a variable in the denominator, and all of the powers are positive integers. Yes? All the powers are positive integers. Okay, so here it asks us, simplify the rational function. If you can, the first thing you should always try to do is factor. So the first thing you should always try to do is factor. Factor both the numerator and denominator. What this allows for you to do is be able to see a lot of key features a lot faster. Okay, first you're going to find the zeros of the numerator and the denominator. Okay. The zeros of the numerator, those are your x-intercepts. The zeros of the denominator, those are going to be your discontinuities. So that's gonna be your asymptote or your whole. Okay, so the numerator tells you your x-intercept. The denominator tells you your discontinuities. Got it? All right, if a 0 isn't common to the denominator and the numerator, you have what's called a hole in your graph. Okay, if the 0 is unique to the denominator only, you have, that's when you have only a vertical asymptote. Okay, and again, reiterating, if the 0 is unique to the numerator, you have it, that's your x-intercept. AKA a root of your function, where you're gonna cross the x-axis. Okay, so each piece of the rational plays a role. Your numerator's job is to tell you your x-intercepts. Your denominator's job is to tell you your discontinuities. But if one cancels the other out, we create a what in our function? A whole. Okay, that's gonna be our stopping place. All we have left tomorrow is to do the full-on example, which I think I'm just gonna do now and record, so that we can start B tomorrow. All right. So for this function, I'm going to follow the steps. I'm going to fully factor. So when I fully factor the numerator, I'm going to factor out GCF is always what I should think. So I factor out x, and I'm left with x minus 3. And the denominator, I'm going to check again. The GCF here is 3x. I factor out 3x, and I'm left with x plus 2. After I factor out, I'm now going to figure out if there's a whole, vertical asymptote, or x-intercept. So when I look here, I do have a factor that can be eliminated. My factor that can be eliminated is x. Because x can be eliminated, that tells me that I have a whole at 0. So I have a whole at x equals 0 because it was eliminated. Okay, then now I'm going to find my vertical asymptote. To find the vertical asymptote, I'm going to use my denominator. And what's left in my denominator is x plus 2. I set that equal to 0. And I get that x equals negative 2 in my denominator. So this is a vertical asymptote. Okay, last is our numerator to find our x-intercept. All I have left in my numerator is x minus 3. I'm going to set that equal to 0, and that's going to give me x equals 3. So that means that I have an x-intercept at 3, 0 is my x-intercept, my root of this function. Okay, so now I have found my x-intercept, my vertical asymptote, and my whole. To be very specific with the whole, I can find the y value of the whole by plugging it back into the original. Well, not into the original, back into the simplified form that I'm left with. So my simplify, I am left with x minus 3 divided by 3 times x plus 2. When I plug 0 into this, I get 0 minus 3 over 3 times 0 plus 2. And that's going to give me negative 3 over 6, which equals negative 1/2. So my whole is exactly located at 0, negative 1/2. And that is something that we should be able to do completely without a graphing calculator and algebra. Thank you.
Hey, bye.